Hello everyone. I will now present our work on how interreflections can be helpful for reflectometry. By reflectometry, we refer to the process of acquiring the reflectance properties of real-world materials as represented by their bidirectional reflectance distribution function. These measured BRDFs can facilitate a variety of applications such as interior decor, industrial design, VR, and AR, where there is an increasing demand for photorealism. In its most general form, the BRDF is a 4D function representing the amount of light a surface reflects for any combination of incoming and outgoing directions. We will discretize this function and visualize it as a 2D matrix for convenience. Probably the simplest reflectometry procedure is to use a Gonier reflectometer. We use a laser and a camera to image a flat material sample from all different combinations of incoming and outgoing directions. Each intensity measurement directly maps to a BRDF entry. Unfortunately, this exhaustive acquisition procedure requires a very large number of measurements to accurately represent the BRDF. It is also possible to modify the acquisition procedure in order to multiplex information about multiple BRDF entries into each image measurement. This can be done by using a curved surface with many normal directions, or by using complex lighting patterns such as spherical harmonics or frequency domain lighting. All of these techniques effectively measure a cross-section of the BRDF with each captured image. While this is more efficient than exhaustive sampling, it still requires capturing potentially hundreds of images. What all of these techniques have in common is that they inherently assume their measurements to be the result of single bounce light transport. Between leaving the light source and reaching the camera, all light paths only reflect once on the material surface. Fundamentally, this assumption allows us to map measurements to BRDF values either directly or at most by solving a simple linear system. Qualitatively, we can categorize reflectometry methods on a spectrum that trades off number of measurements with computational complexity. In this spectrum, existing methods almost exclusively occupy the left side. This motivates the following question. Can we devise a reflectometry method that is on the other end of the spectrum, allowing high fidelity BRDF recovery from very few measurements at the cost of increased computational processing? Our main goal in this work is to show that this can be achieved by moving away from single bounce assumption and taking advantage of interreflection effects. For some insight, let's say we use a concave shape for reflectometry. Each image measurement will sum contributions from not only single bounce paths, but also from two bounce and higher order paths. The contribution of a two bounce path will be a function of two entries of the BRDF, one for each reflection event. A three bounce path will involve three entries of the BRDF and so on. Consequently, just a single image can provide us with information about a very large set of BRDF entries. However, the relationship between measurements and BRDF values is highly nonlinear and can no longer be trivially inverted. In the rest of this talk, I will show you how to overcome this obstacle in order to make reflectometry from interreflections possible. I will first discuss an analysis by synthesis framework that uses differentiable rendering to solve for BRDF representations from a single image containing higher order transport effects. I will show simulated experiments where we combine this framework with a suitable BRDF parameterization to recover high fidelity BRDF measurements. Finally, I will discuss how to quantify the effect of shape on the quality of the BRDF recovery. Our measurement setup is fairly simple. We capture a single image of a surface of known shape using calibrated directional illumination and an orthographic camera. We then perform analysis by synthesis. We search for a BRDF that, when used with a simulator, can reproduce the measured image. Given as input the calibrated scene parameters and the BRDF hypothesis, our simulator must be able to reproduce the high-order transport effects present in our measurements. Additionally, to enable efficient optimization of the highly nonlinear loss of analysis by synthesis, the simulator should also compute derivatives of images with respect to the BRDF. We achieve both of these objectives by using a Monte Carlo differentiable renderer, which we have implemented on top of the bidirectional path tracer of Mitsuba. We can now turn our attention to the next component of our analysis by synthesis framework, the BRDF representation. The non-parametric 4D form of the BRDF, while very descriptive, can be unwieldy for optimization. Instead, we want to use a more compact but still descriptive BRDF representation. We adopt a linear basis parameterization that has been common in the reflectometry literature. For this, we select a set of basis elements, each corresponding to a valid BRDF. Then we can approximate any unknown BRDF as a linear combination of these basis elements by recovering the mixing weights W that produce the closest match to image measurements. For our basis, we use 40 BRDFs computed to best fit the Merle database. A key point here is that for a non-convex surface, images rendered with each of the basis BRDFs do not mix linearly. This makes it necessary to use Monte Carlo differentiable rendering to optimize for the mixing weights. Let's see some results. We begin with a simple example that demonstrates the rich information that can be obtained by using interreflections. We consider a tetrahedron, imaged with an orthographic camera and a directional light source. As the tetrahedron has only 3 visible faces, the captured image will be the result of reflection at only 3 angles, and will provide us with only 3 constraints on the BRDF. We additionally consider the concave side of the same tetrahedron. Thanks to the paths that reflect multiple times at its interior, a single image in this case will provide us with significantly more constraints on the BRDF. To quantify this, we use our optimization framework to recover a synthetic material represented using bases with different numbers of elements. When our basis has 3 elements, and therefore our BRDF has only 3 parameters, both convex and concave shapes provide sufficient constraints to correctly recover the unknown BRDF. However, as we increase the number of basis elements, the convex case becomes under-constrained and the BRDF recovery is unsuccessful. By contrast, in the concave case, the BRDF recovery remains just as accurate even when we increase the number of atoms to 5, 10, or even 40. In practice, instead of a tetrahedron, we would use a more informative shape for reflectometry, such as a sphere. By having a different normal at each surface point, a convex sphere provides us with many more than 3 constraints on the BRDF. Even in this case, the concave sphere provides still more information about the BRDF thanks to the interreflections. We can quantify this by comparing the BRDF reconstruction accuracy achieved using a single image of each of the 2 shapes. In the results that we show, the unknown BRDF comes from the MERL database, and we visualize both the ground truth and the 2 recovered BRDFs by rendering the images of a common shape under environment map illumination. Using the concave sphere improves single-shot BRDF parameter recovery by approximately 6.3 times across the entire MERL dataset when compared to the convex case. As we can observe from these results, what shape we use has a strong effect on the accuracy of BRDF recovery. This motivates 2 important questions. First, how can we systematically characterize how informative each shape is for reflectometry? And second, how can we design an optimal shape that maximizes the amount of information on the unknown BRDF available in a single image measurement? In the rest of the talk, I will show some first steps that we have taken towards answering these questions. To simplify analysis and visualization, we will adopt the so-called bivariate representation, which expresses a BRDF as a function of only 2 angles θ h and θ d defined as follows. Consider the vectors omega in and omega out representing the incoming and outgoing light directions. The half vector h is the direction vector corresponding to their bisector. The angle between the half vector and the normal vector is θ h, and the angle between the omega in and omega out is θ d. We can use the bivariate representation to visualize BRDFs as 2D matrices. We show this for 2 example BRDFs along with the representative images rendered with these BRDFs. In each table, the top part corresponds to near specular reflections, with the top left region being near normal incidence and the top right region being grazing incidence. We can use the bivariate representation to visualize which parts of the BRDF are being sampled using different shapes. Let's look at the convex and concave tetrahedra we considered earlier. If we consider only single bounce paths, then both shapes sample only 3 entries in the bivariate table corresponding to the 3 visible faces of the tetrahedron. However, as we consider paths with more than 1 bounce, we see that the concave shape samples a much larger part of the bivariate table, providing a lot more information about the BRDF. Now let's consider the convex and concave sphere shapes. Single bounce paths only sample 1 column of the bivariate table corresponding to the constant θ d angle between our fixed illumination and viewing directions. As before, when we consider paths with more than 1 bounce, the concave shape allows us to sample a much larger part of the bivariate space. We note, though, that even the concave sphere cannot sample the part of the bivariate space corresponding to specular reflection at normal incidence. This motivates the question, can we design a shape that improves the coverage of the bivariate space? We show one simple procedure for producing such a custom shape through 2 design goals. First, we want our shape to provide strong coverage of the specular part of the bivariate space. This is the part where we expect the BRDF to have high and rapidly changing values, and thus has a dominant effect on the appearance. Second, we want this coverage to be achieved through paths of no more than 2 bounces, as higher order paths will have smaller contributions to the overall image. To simplify our design procedure, we assume that the incoming and outgoing directions are the same. We start off the design of our custom shape using a half sphere, which helps maximize the coverage from single bounce paths. We design the rest of the shape as follows. For any given ray from the camera, taking into account our first design goal, we consider its specular reflection on the half sphere. The reflected ray will intersect the unknown part of the shape at some point where another reflection will occur. We know that the resulting ray must go towards the light to form a two-bounce path. Finally, from goal 1, we select the unknown normal at this point to correspond to the mirror reflection. Repeating this process for all camera rays gives us a set of normal constraints. By integrating these normals, we can form a final shape that is shown here. We can use the same bivariate representation as before to visualize the information our custom shape provides for reflectometry. Compared to the concave sphere, we observe that our shape achieves much more uniform coverage of the bivariate space, including coverage of the top left specular part. We can also perform simulated reconstruction experiments to see how this improved coverage affects BRDF recovery quality. We show single-shot recovery experiments for a few BRDFs from the Merle database. Using our custom shape, we can achieve 11.2 times more accurate BRDF recovery than when using the convex sphere, and 2 times more accurate recovery than when using the concave sphere. To conclude, let me summarize a few key takeaways from our paper. First, we have shown that higher order transport effects can provide rich information for reflectometry, allowing us to significantly reduce the number of image measurements required. Second, we have shown that the combination of analysis by synthesis with physically accurate differentiable rendering can help us solve the very nonlinear inverse problem required for recovering the unknown BRDF. Thirdly, we have highlighted the important effect different concave shapes can have on the BRDF reconstruction quality. We have shown how to design one kind of shape that is well suited for reflectometry, and we hope that our work will motivate significant additional research on discovering optimal shapes for this application. Thank you for your attention. Please visit our website for code and additional results.